All right, welcome everyone. Today we're going to tackle two really fundamental concepts for series circuits. First, we'll get a solid handle on how to calculate the total power. And second, we're going to demystify voltage measurements by really digging into the crucial idea of a reference ground. So let's jump right in. So our first principle is, thankfully, pretty straightforward. In any series circuit, the total power consumed is simply the sum of the power used up by each individual component. You literally just add them all up. Nice and easy. And this slide really lays out that rule for us. You can see that total power is just P1 plus P2 plus P3, and so on for however many components you have. Now, to calculate that total power directly, you've got three main tools in your toolbox. You can use source voltage times current, you can use current squared times the total resistance, or you can use the source voltage squared divided by the total resistance. Theory is great, right? But let's see this stuff in action. We're going to take a circuit and calculate its total power using two different methods, just to prove to ourselves that this additive principle really works. Okay, here is our circuit for this example. We've got a 15-volt source powering 4 resistors connected in series, a 10 ohm, an 18 ohm, a 56 ohm, and a 22 ohm. Our mission is to find out the total power being dissipated by this entire circuit. Let's start with the most direct way. First thing we got to do is find the total resistance. Since they're in series, we just add them up. 10 plus 18 plus 56 plus 22, that gives us 106 ohms. Easy. Now we just grab our power formula, P equals V squared over R. So that's 15 volts squared, which is 225, divided by our 106 ohms, and that gives us a total power of 2.12 watts. Okay, so that's one way to get the answer. But to really prove our rule, are we going to get that same 2.12 watts if we do it the long way? Calculate the power for each and every resistor one by one, and then add them all up at the end. Let's check it out. So for this method, the first thing we need is the current flowing through the circuit. Simple Ohm's law. 15 volts divided by our total resistance of 106 ohms gives us about 142 milliamps. Now for the grunt work. We use the formula P equals I squared R for each resistor to find their individual power consumption. And when we add them all up, 200 milliwatts plus 360 plus 1.12 watts plus 441 milliwatts, what do you know? We get exactly 2.2 watts. It's a perfect match. The rule holds true. Now, knowing how to calculate power is a vital skill, but it's only half the story. In the real world, out on the lab bench, every single component has a physical limit that you absolutely must respect, and that's its power rating. Take a look at this circuit diagram. See that little half W label next to each resistor? That's its power rating. Think of it as a speed limit. It's the absolute maximum amount of power that resistor can safely dissipate as heat before it gets damaged or, more likely, just smokes and burns out. So let's run a safety check on this circuit. The current here is 15 milliamps. When we calculate the power for each resistor, R1 and R3 are fine. They're well below their 500 milliwatt or half-watt rating. But look at R2 and R4. R2 is trying to dissipate 608 milliwatts, and R4 is trying to get rid of 743. That is way over their rating. I guarantee you, if you build this circuit, those two resistors will burn out. You'll probably smell it. All right, let's completely switch gears. We've got power down. Now we need to tackle our second big concept, and this one's a bit more abstract. We're talking about reference ground, and I promise you, this idea is the key to truly understanding any and all voltage measurements. So what in the world is reference ground? Well, it's actually pretty simple. It's just a point in the circuit that we, as the designers or the technicians, decide to call 0 volts. That's it. It's our anchor point. Every other voltage we measure in that circuit is simply the potential difference between some point and that 0-volt reference we chose. A perfect real-world example of this is the electrical system in a car. The negative terminal of the battery is literally bolted directly to the car's metal frame. By doing this, the entire metal chassis of the car becomes the reference ground. It's the common 0-volt return path for everything. And this brings us to the big aha moment about ground. Its location is completely arbitrary. Changing where you place that ground symbol doesn't change how the circuit actually works one bit, but it completely changes the voltage values that you'll measure with your meter. Now look very closely at these two diagrams. They are showing the exact same circuit. Same voltage source, same resistors, same current flowing through it. The only thing that's different is where we've placed that little ground symbol. On the left, it's at the very bottom. On the right, we've moved it up to the middle. And here's what happens because of that one little change. Look at point A. With ground at the bottom, your meter would read plus 12 volts. But when we move the ground to the middle, that same physical point now reads plus 6 volts. And look at point C. It goes from being plus 4 volts to being a negative 2 volts. Now, the key thing to realize is that the voltage drop across each resistor hasn't changed at all. But the voltage at each point is completely different, all because we moved our zero reference. And this isn't some weird fluke. This is a fundamental property of voltage. In these three examples, you can see how as the ground point moves from E to D and then up to C, all the other voltage readings just shift right along with it. It just proves the point. Voltage is always, always relative to your reference. Okay, this is all well and good on paper, but how does this actually translate to the lab bench when you're taking real measurements? Let's connect this theory to the actual tools you'll be using every day. So, picture this. You've got your circuit built on a breadboard, you've got a multimeter in your hand. How do you actually measure a voltage with respect to ground? Here's the absolute key. On your digital multimeter, you'll see that the black probe is plugged into the jack labeled COM, which stands for common. That black probe is your reference point. So if you want to measure the voltage at point B with respect to ground, you literally connect the black probe to your circuit's ground point, and then you touch the red probe to point B. The meter does the rest. And it's the exact same principle for an old-school analog meter. The black lead is your zero reference. The meter's needle is just showing you the potential difference between where the red probe is and where the black probe is. Where you put that black probe defines what 0 volts means for that specific measurement. So let's end on a little thought experiment for you. If you measure the voltage from point B to point C, meaning red probe on B, black on C, and your meter reads a positive 4 volts, what do you think it will read if you swap the probes? What's the voltage from C to B? The answer really comes down to which probe is your reference. Mull that over before your next lab session. Hello, everyone, and welcome. You know, as a professor, I see this happen every single semester. A circuit makes perfect sense on the whiteboard, right? But the moment you get to the lab bench, things get complicated. Well, today, we're going to bridge that gap. We're going to master the practical skills you absolutely need to take series circuits from theory to reality. Let's get started. So look at this. On the left, that's the world of theory. It's clean, it's perfect, it's predictable. Every value is exactly what it says it is. But on the right, well, that's the lab bench. That's the real world. You've got your breadboard, your tangled wires, your multimeter, and physical components with all their quirks and tolerances. Our job, as engineers, is to make the thing on the right behave exactly like the diagram on the left predicts it should. And how do we do that? Well, it really boils down to mastering two core skills. First up, power analysis. This is all about understanding the why and how much. It's about making sure your components don't literally go up in smoke. Then, second, we've got voltage measurement. This is mastering the how, and more importantly, from where. This is the absolute key to troubleshooting your circuits. You get these two things right, and trust me, you are well on your way. Okay, let's kick things off with power. Now, power isn't just some abstract number you calculate for homework. In the real world, every single component has a physical limit to the amount of heat it can safely get rid of. If you exceed that limit, you're going to have a component failure. And the so what here is huge. An overloaded component isn't just a broken part. We're talking about a potential fire hazard. And this is what happens when you ignore those power ratings. The resistor on the right was asked to dissipate way more power than it was designed for. And the result? Catastrophic failure. You can practically smell it through the screen. The key principle to burn into your memory, no pun intended, is that in a series circuit, the total power from the source equals the sum of all the individual powers being used up by each component. So how do we actually analyze this? Well, the first way is what I call the big picture approach, a system-level analysis. You find the total resistance of the whole circuit. In this case, it's 106 ohms. Then you use your trusty power formula, P equals V squared over R. With our 15-volt source, a quick calculation tells us the entire circuit is going to draw 2.12 watts. This is a great first step for sure. It tells you your total energy budget. But, and this is a huge but, that's not the whole story. This is method 2, component-level analysis. Now here's my professor's pro tip for you. This is the essential step. The first method is faster for total power, yeah, but this method is what saves your parts. You have to calculate the power for each individual resistor. And if you look closely here, you can see that resistor R3 is trying to dissipate 1.12 watts all by itself. So let's apply this to a real scenario. Here we have a circuit where every single resistor is rated for half a watt, or 500 milliwatts. We run the numbers. R1 is dissipating 225 milliwatts. We're good. It can handle that. But then we get to R2. Uh-oh. It's trying to dissipate 608 milliwatts. That is over its rating. It is going to fail. And R4? Even worse, at 743 milliwatts. So the crucial takeaway here is that your analysis just proved these parts are underspecified. They have to be replaced with resistors rated for at least 1 watt to be safe. All right, that's power. Let's switch gears and move on to our second module, voltage. Now, measuring voltage on the bench brings up a really fundamental question that, honestly, can be super confusing if you don't grasp the core concept. It's all about perspective, it's all relative. And this is it, right here. When you see plus 5 volts on a diagram or you measure it with your multimeter, that number is completely meaningless by itself. See, voltage is not some absolute value floating in space, it is a potential difference between 2 points. So the unspoken question is always relative to what? And the answer to that question is your reference ground. To make this idea really stick, think about your car. The negative terminal of the battery is bolted directly to the metal frame, the chassis. That means the entire metal frame of the car becomes the common 0-volt reference point for everything. So when we say the positive terminal is at plus 12 volts, what we're really saying is it's plus 12 volts relative to the chassis. It's that simple. Okay, now this is where it all clicks into place. Look at these 3 circuits. They are physically identical. The only thing that's different is where we, the engineers, have decided to place our 0-volt ground reference. Now look at the table. Notice how the voltage at point B changes from plus 8V to minus 4V to plus 2V. The numbers are totally different. But, and this is the absolute crucial insight, the voltage drop across any one component, like R2, stays constant at 4 volts in every single case. The physics doesn't change, only our measurement perspective does. So, when you're at the bench, multimeter in hand, how do you do this professionally? It's a simple, repeatable process. Step 1. Set your multimeter to DC voltage. Step 2, and this is the most important part, connect the black probe, the COM or reference probe, to whatever you've defined as your circuit's ground point, and it stays there. You anchor it. Step 3, you take the red probe and you touch any point you want to measure. The number on the screen is the voltage at that point with respect to ground. And if you see a negative value, that just means that point is at a lower potential than your ground reference. No big deal. Okay, time for a quick challenge to see if you've got it. Here are 3 identical circuits, but I've moved the ground point on you. Go ahead and pause this explainer for a moment and see if you can figure out the voltages at each node relative to the new ground. Ready? Okay, as you can see in circuit B, grounding at point D makes it 0 volts, which means point A shoots up to plus 75 volts. Then in circuit C, we ground at C, and now A is only plus 50 volts relative to our new reference. See? It's all about perspective. So let's wrap all this up with a quick debrief. We've covered a lot of ground, really bridging that gap between the classroom and the lab bench. If you walk away remembering only a few things, please make it these key engineering takeaways. First, power dictates survival. Don't just calculate the total power. You must check the power being dissipated by each and every component and compare it to its rating. Second, voltage is a difference. A single number like plus 5V means absolutely nothing without knowing the reference point it's measured against. And third, ground is your anchor. You, the engineer, get to decide where that 0-volt reference goes. Your choice will change the numbers you read, but it will never, ever change the physics of the circuit. You see, mastering these fundamentals, power analysis and reference-based measurement, that is the bridge that takes you from sketching simple circuits on a whiteboard to designing and building reliable, functioning systems in the real world. So the final takeaway is this: analyze your design, verify it using these principles, and you will be able to build with confidence.